Just take a look around you. I mean, right now, the phone or computer you're watching this on, the windows in your room, even the air you're breathing, it's all made of elements. But here's the thing, all those elements pretty much fall into two huge teams. And that one simple fact explains almost everything about the world we live in. Today, we are diving deep into that massive split, metals versus nonmetals.
Seriously, think about that for a second. Why is it that you can take a piece of gold and hammer it into a super thin sheet, but if you try that with a piece of charcoal, which is also an element by the way, it just explodes into dust? They couldn't be more different, right? Well, the answer gets right to the very heart of chemistry.
And that's it. That's the secret. It is this fundamental divide between metals on one side and nonmetals on the other. This one classification is the master key to understanding why materials behave the way they do. So let's break it down and see what actually makes them tick.
Okay, we're going to start with the most obvious stuff, the things you can literally see and touch. We're going to put their physical properties head-to-head in a little showdown.
First up, just looks. You know it when you see it, right? Metals have that classic shine. Chemists call it metallic luster. It's that gleam you see on a polished spoon or a gold ring. And nonmetals? Well, they're usually the exact opposite. Think about the dull, flat look of a piece of coal or a pile of sulfur. No shine at all.
But, and this is what makes chemistry so much fun, it loves to break its own rules. Check out iodine. It is 100% a nonmetal. But look at it. It's got this incredible, shiny luster that could fool anyone into thinking it's a metal. It's the perfect reminder that these are really good guidelines, but not unbreakable laws. All right, next up, hardness. You know, our gut feeling tells us metals are tough. We think of steel beams, iron skillets, and for the most part, yeah, that's totally right. Nonmetals, on the other hand, tend to be pretty soft. And then you get the exceptions. And wow, are they spectacular. There are metals like sodium that are so soft you can literally slice them with a butter knife. And on the complete flip side, you have diamond. Was it made of? Carbon, a nonmetal. And it is the hardest natural thing on the entire planet. How cool is that? Now we get to two words that are absolutely crucial for understanding this whole thing: malleability and ductility. Malleability just means you can hammer it into thin sheets. Ductility means you can pull it into a wire. And metals are the champions of both. Nonmetals, they're the opposite. They are brittle. You hit them, they shatter. And that right there is the answer to our first question about why you can shape gold but not charcoal.
And to give you an idea of just how ridiculously ductile some metals are, get this. From a single gram of gold that's smaller than a pea, you can draw a wile that is 2 kilometers long. That's just mind-blowing.
Okay, so we've got a handle on what they look and feel like. But what happens when they actually start reacting with things? This is where we get to the chemical contest. To figure all this out, scientists came up with something called the reactivity series. Honestly, the best way to picture it is like a ladder or a league table for metals. At the very top, you have the most reactive ones, like potassium, that are just desperate to get into a chemical reaction. And way down at the bottom, you have the super chill, unreactive ones, like gold. And this ladder perfectly predicts how they'll react with something like oxygen. At the top, potassium and sodium are so reactive, they literally burst into flame if you expose them to air. That's why you have to store them in kerosene. As you go down the list, the reactions get less and less dramatic, from magnesium's dazzling white flame all the way down to gold, which does nothing. It doesn't react at all, and that's why your gold ring never rusts. Okay, here's a fun little chemical puzzle for you. If you drop a piece of calcium metal into water, it fizzes away and it floats. But wait a minute, calcium is a metal. It's way denser than water. It should sink, right? So what's going on? The answer is actually pretty simple and kind of brilliant. The reaction itself creates hydrogen gas, and those little bubbles of gas cling to the surface of the calcium, making it buoyant enough to float. It's like it's wearing thousands of tiny invisible life jackets. So we know these metals have all these amazing properties, but how do we actually get our hands on them? They don't just pop out of the ground in perfect shiny bars. We have to work for it. We have to extract them from the earth. The whole process has a name, metallurgy, and it's basically a 3-step recipe. First, you have to concentrate the ore, which is just a fancy way of saying you get rid of all the useless dirt and rock, which, by the way, is called gangue.
Then comes extraction. That's the key chemical step where you finally free the metal from the mineral it's trapped in. And last, you refine it, purifying that raw metal into the good stuff we can actually use.
Now, during that extraction step, you'll often hear about two methods, roasting and calcination. They both involve heating the ore, but there's one critical difference: oxygen. Roasting is for sulfide ores, and you use a ton of air. Calcination is for carbonate ores, and you use very little air or none at all. The end goal for both is the same, though: turn the ore into a metal oxide, because that's way easier to work with for the final step.
All right, so we've spent all this time treating them like total opposites. But what happens when a metal and a non-metal finally come together and react with each other? Well, this is where some of the most important compounds in the world are born.
So let's take a classic metal, sodium, and a classic nonmetal, chlorine. If you look at their electrons, you see sodium has this one lonely electron in its outermost shell, and chlorine has 7. Neither of them is happy like this. What all atoms want more than anything is to have a full outer shell, to be stable.
And this is where the magic happens. It's a perfect match. Sodium, the metal, doesn't want its extra electron, so it just gives it away. And chlorine, the nonmetal, desperately needs one more, so it takes it. Suddenly, sodium becomes a positive ion, and chlorine becomes a negative ion. And what do opposites do? They attract. This powerful magnetic-like force between them is called an ionic bond.
And that incredibly strong bond is what gives compounds like table salt their unique properties. It's why they form these hard, solid crystals with super high melting points. But that rigid structure is also why they're brittle, and it's why they only conduct electricity when those ions are free to move around, either when you melt them down or dissolve them in water.
So let's bring all this theory back down to Earth, because understanding all these properties isn't just for a chemistry test. It lets us do incredible things, to engineer materials to do exactly what we want them to do, from the copper wires in our walls to the jewelry we wear. And that brings us to a perfect real-world example. Why isn't most jewelry made of pure 24-karat gold? Well, because pure gold is actually pretty soft. If you made a ring out of it, it would bend and scratch really easily. So what's the solution? You make an alloy. You mix that soft gold with a harder metal, like copper, to make it more durable. That's what 22-karat gold is, and it's way better for making things that last.
So there you have it, from the amazing ductility of the copper in our wiring to the incredible hardness of a diamond on a ring. This fundamental split between metals and nonmetals really does explain the world all around us. So the next time you pick something up, take a second, think about it. Now that you know the rules of the game, what other materials around you can you explain?